Hi everyone, welcome to TI High Voltage Seminar. Today, Shamim and I are going to talk about managing power conversion challenges in microinverters. My name is Fengkun Liu. I'm currently the Applications Manager on TI GaN team. Shamim?
My name is Shamim Chaudhary. I'm part of the C2000 microcontroller systems and application team here in Sugar Land, Texas.
Yeah, thank you, Shamim. So for the agenda today, I will start with a general introduction about microinverter, and then from the hardware point of view, talk about the structures and the topologies. Based on this background, I will also introduce why we believe GaN is the best power switches in this kind of application based on a typical application design case. For the materials about hardware here, many of them are from TI System Engineering and Marketing team, Ricardo Rufo from Harold Pajuber's team, Pajuber's group, and Emma Wang from the field team. I also want to thank them for the contributions here. After the hardware discussion, I will handle the ball to Shamim, and he will talk about the control and firmware challenges in different stages and how we can approach them. Okay, let's go to first, what is microinverter? For solar energy systems based on the different structures of PV panels and the optimizer inverter stages, there are different types of inverters. The string inverters and also the central inverters, these are like one inverter will serve as the inverter for a considerable amount of panels. This is commonly seen in the PV farms where you have some considerable amount of PV panels there for the solar energy. On the other hand, microinverter, you will put only one inverter for up to 4 panels, or even just 1 panels of the PV. This is commonly used in the household because you will only have limited number and a number of PV panels you want to put it on your rooftop. So here's a more detailed overview of the microinverter. The power level of it is normally below 2 kilowatts. But we are also seeing the market is moving to higher and higher power, like up to 3.6 kilowatts these days. Microinverter itself is used to convert the PV panel output DC power to the AC grid power. It always has a MPPT stage right after the PV panel to maximize the PV output power. Microinverter also needs to have a transformer to provide the Gavale isolation from the grid, and normally it's on the DC-DC stage. And it also needs a DC-AC stage, inverter stage, to complete the conversion. Here is a diagram for the configuration. Traditionally, unidirectional DC-DC stage and AC-DC stage is good enough. However, for the market, there's a new trend to combine the PV system together with the energy storage system. In that way, it can provide more benefits like regulating the power consumptions if you have different prices for the electricities from day to the night. So in this case, bidirectional operation on a bidirectional DC-DC converter and AC-DC converter is required. For the topologies of this microinverter, the AC-DC stage, as an inverter, there are two basic topologies of kind of inverters. One is current source inverter, another is voltage source inverter. Traditionally, current source inverter plus flyback-based flyback-based solution is a traditional way of doing the microinverter. However, considering the requirement of energy storage system integration, the voltage source inverter is more preferred these days because it has a DC bus there so that you can do the energy storage from it. So today I will be more focusing on the voltage source inverter application and discussions here. So for the VSI topologies, two-node pole, AC/DC, and H-bridge inverter solutions with different modulation, including the unipower solution, unipower technical and bipolar technical are most common ones. Parent inverter, on the other hand, it has its own advantage, but right now it has some limitations for widespreading because of the IP loyalty. And for all this system, it is best to work with TI C2000 digital controller solutions, which can give you the entire solution for all the stages. Shamim will get into more details for the second half of this presentation today. Okay, let's get back to the hardware. As we are talking about H-bridge converters, GaN is always the best in this kind of structure. So let's talk about the traditional silicon approach, why they are not suitable for H-bridge first. The traditional silicon MOSFETs, they will suffer a lot from the reverse recovery. You can see for this kind of symmetrical H-bridge structure, when you have the switching, the through will happen due to the reverse recovery of the silicon body delt. And also, this will result in some risk of failure. That's first thing. Second thing, this reverse recovery is additional loss on the device, and this is a considerable large amount of loss that make silicon MOSFET and IGBT cannot operate at very high switching frequency. With CCM operation, if you use CM, just it's possible, but CM also has its own trade-off there. So, but for GaN, you do not need to worry about that because the GaN FET itself doesn't have any reverse recovery loss. In that case, that can minimize your symmetrical bridge performance in a continuous conduction mode. For silicon carbide, although the reverse recovery for that is small, but it's not as good as GaN as well. So GaN is definitely the best choice here in these H-bridge based solutions. We can see more details about GaN devices here. So for the loss inside the device, GaN itself, because of the material property, the figure of merit GaN is a lot better compared with silicon. So the GaN device will have lower COSS loss with the same ADSON. And as I mentioned, since there are no body delt, there's no reverse recovery related loss. So the loss from the device can be minimized with GaN adoption. There are more details illustration on the switching performance as well. For the same ADSON, GaN can realize a relatively smaller overlap loss comparing with silicon carbide. That makes the switching performance of GaN better so that you can improve your overall system efficiency. For TI GaN, actually we are developing the GaN technology together with based on our several decades of experience on the analog devices, especially on the driver design. We are not doing the device itself, we are actually doing the driver integrated solution so that when you do this kind of very fast speed switching, the influence from parasitic parameters like all the inductors can be minimized. The driver, we integrated the very powerful TI driver with the GaN FET into our GaN product. To realize a very small parasitic, you can see that's only less than 1 nanohenry common source and less than 4 nanohenry gate loop inductance, so that we can maximize the capability of switching speed of GaN. And by having this kind of integration, we can also integrate a lot of different protection features to the device, like the overcurrent protection, short circuit protection, over temperature protection, so that will help improve the robustness of your system. Let's get into a more detailed study on the hardware on a microinverter case and show how is the performance of GaN comparing with other available power semiconductor choices. So here is a comparison study done by Ricardo, as I mentioned. He compared the GaN solution versus silicon carbide solution and IGBT solution in this 3.6 kilowatt platform with H-bridge unipolar, H-bridge bipolar, and two-tone pole and Henry converter. By that one, the efficiency at peak power is fixed to be one parameter, and the different devices are considered in this study, including the IGBT FET with TO247 package, another is silicon carbide FET, and the TI GaN FET. This is a 30 milliohm 650 volt device. Comparing with silicon carbide device, compare the GaN devices with silicon carbide device. Silicon carbide device will have some advantage over conduction loss because of the temperature efficiency, temperature coefficient. But for the GaN, the switching performance is better. When you combine, so there is some trade-off in the designs. And for this analysis, basically, the switching frequency is swept to find the best switching frequency that can meet that high, that efficiency target, so that will be the optimized data operating point for each of the device. This study, this is one example of in this H-bridge unipolar PWM modulation, how the approach looks like. The similar study also done on the other cases, including the H-bridge bipolar, the two-tone pole, and also the Henry. Here comes the comparison result. You can see among all these, comparing with silicon carbide solution, GaN solution can have the better optimized switching frequency so that your inductor size can be reduced. At the same time, GaN will offer a better CEC efficiency comparing with the same optimized silicon carbide solution. The CEC efficiency is actually the California Energy Commission weighted efficiency. So this value is, some kind of weighted efficiency combination for the efficiency at different load condition. From this comparison, you can clearly see how GaN can help you improve the efficiency as well as reduce your passive component size. The last point I want to talk about is on the thermal solution. Comparing with traditional, comparing with other AC/DC solution like the PSU market, the thermal solution for PV inverter microinverter will be different. For the PSU, they are using fan, but for microinverter, there is no fan associated with them. So purely we need to use the tin material plus hissing GaN gel to solve the problem. With that, actually, we offer some kind of loss calculation sheet online. So you can use that to estimate how much loss that will produce in different PV systems. And based on the loss estimation, you can come up with the best design for your system. Okay, I think that's all the materials I hope to cover on the hardware side. I will then handle the ball to Xiaoming, and he will introduce on the firmware and control side. Xiaoming, it's your turn.
Good afternoon. I will talk about the control aspects and control challenges in microinverter control. The outline will be, we'll first talk about the MPPT stage, and then the inverter stage, and also the communication between the microinverter and the gateway. So the challenges in microinverter control, we're talking about digital implementation using available microcontroller in the market. So digital implementation, the first goal of microinverter is to achieve very low THD grid current. Grid current injected should have very low THD. That requires high bandwidth current loop control. With higher bandwidth, you can reduce the THD, and that again, high bandwidth control loop requires fast digital control loop, fast calculation, and which in turns require a fast microcontroller optimized for digital control application. It is fast processor plus optimized control implementation that reduces the latency in the control loop, that will be able to achieve very high bandwidth and in the end very low THD grid current. The second aspect is high efficiency and high power density is also very much desired. High efficiency, high power density will require advanced power topologies running at higher frequency, very high frequency. Advanced power topologies translates to a very flexible PWM generation scheme in the microcontroller, so that all kinds of different PWM waveforms can be generated from the microcontroller. High frequency PWM, high resolution with high duty cycle resolution, frequency resolution, phase shift, and dead time resolution is required to achieve high frequency PWM. Low latency, as I said, low latency, fast, high frequency digital control loop. So you can sense the signal and quickly implement, get into the interrupt service routine and do all the calculation, and then update the PWM properties, either duty cycle or frequency or phase shift, whichever. So that latency has to be minimized and minimized as best as possible to reduce the delay in the control loop. And on top of that, the processor has to run, has to be high CPU, high horsepower processor, so that you can run the control implementation quickly. Third thing is the maximum power point MPPT tracking from the panel, which maximizes the return from the installation. That is also desired. That requires small ripple across the PV module, so that the MPPT point to operate around the MPPT point without any fluctuations. To stay in the MPPT point, the ripple has to be minimized also. Then you can calculate the MPPT point and stay at the MPP point to achieve maximum power point, extract maximum power. Fourth thing is the accurate estimation of grid phase. Inverter output current has to be in phase and frequency locked to the fundamental grid voltage, and that translates to low THD and high power factor current injection into the grid and maximize power. In some cases, you also may need to control the reactive power, and that will also be implemented with the phase lock loop. So accurate estimation of the grid phase is important to be able to achieve all this. Next is the decoupling of power. In the DC side, you have the PV side, you have the DC power. In the AC side, you have the DC plus double frequency ripple. So in between, you need some kind of decoupling capacitor to reduce the storage element so that the double line frequency cannot disturb the PV side. Electrolytic can be used, but electrolytic, because of higher reliability, it is desired. Electrolytic free capacitor is desired, so that implies capacitance, if can be minimized, so that film capacitor can be used instead. The last is also a communication between microinverter and the gateway. PLC is one way to achieve that, and also that requires microcontroller with enough processing power so that microcontroller can implement the PLC communication on the same chip. So microcontroller having enough processing power can implement all these three function: MPPT function, and then the inverter function, and then power line communication function. So if we look at the MPPT control here, MPPT algorithm uses the PV panel, IPV, current, and the PV panel voltage, VPV, and implements the reference voltage that based on the maximum power point, and feeds into the PI loop, outer voltage loop. You can see the PI controller, reference voltage and the feedback PV voltage is compared, and high bandwidth PI loop is used to generate the reference current, and then that current gets compared with the feedback current again, and another PI controller to control the current in the MPPT stage. And finally, PI output generates the PWM signal for the DC-DC MPPT boost converter. So here's the outer voltage loop. Outer voltage loop regulates the input voltage and maintains the input voltage at the maximum power point, reference voltage generated by the MPPT algorithm. The second thing is the another current loop here controls the closed loop current for the boost stage to maintain the loading of the panel. Now here, in this case, we don't necessarily regulate the output voltage of the boost stage. Is the input voltage is being regulated. However, OVP is implemented using the internal comparator in the microcontroller or some external comparator if it doesn't have any, and the cycle by cycle trip feature for the control MCU. The downstream inverter will make sure the MPPT stage is loaded and it draws enough power from the MPPT stage so that bus voltage over voltage doesn't happen. But so it's not output voltage control, is input voltage of the boost converter is being controlled in this case. So MPPT algorithms, there are several are used today in industry. One of them is the perturb and observe PNO algorithm, where panel voltage reference is continuously perturbed and the change in power is observed. Perturbation that leads to increase in power is rewarded. Otherwise, the direction is basically reversed. So you can see the PNO power versus panel voltage curve. So it generates the maximum power point voltage where the power is maximum. So that's the PNO algorithm. On the right side, you can see another algorithm is incremental conductance, INCC, which basically measures the slope of the power curve. The slope of the PV panel power curve, as you can see, is zero at the maximum power point and positive on the left side of the MPP point, and the negative on the right side of the MPP. So this information is used to calculate the VMPP reference PV voltage and maintain the operation at the PMPP point, as you can see. So these are two algorithms. There are other algorithms can be used. So this requires some computation by the microcontroller that will implement these algorithms from a slower loop or in the same loop as in the boost DC-DC stage controller. Inverter stage commonly used a full bridge type inverter. It generates, as we said, clean sinusoidal waveform and connects to the grid. It injects a clean current to the grid. The full bridge inverter generates high frequency sinusoidal waveform, which is then filtered by the LCL filter, mostly used. Output filter generates the 50-60 Hertz AC waveform. LCL filter is commonly used to attenuate the harmonics in grid-connected application. One way to solve the LCL resonance is to use adaptive fourth-order notch filter in the control implementation. Tuning and connecting to the grid remains another challenging issue. Tuning of the current loop of the inverter, and in that case, a software-based integrated frequency response analyzer (SFRA) greatly simplifies the process of tuning. So, software frequency response analyzer can be used and to tune the current loop, look at the Bode plot and the stability, and then it can optimize the control and implement a good stable control loop for good low THD current. So that can come as a handy tool, and microcontroller that can implement such a software-based frequency response analyzer comes handy in terms of it eliminates the external equipment, and the integrated software-based frequency response analyzer can be used to verify the control loop stability. PWM configuration in microinverter can be made two types basically. One is the both DC-DC and inverter stage uses high frequency PWM control. So DC-DC boost uses high frequency, inverter stage also uses high frequency PWM. A constant voltage DC-link decouples the power flow, as we said before, in the two stages, such that the DC input in the PV side is not affected by the double line frequency power that happens on the AC side of the inverter. So that's one way PWM control is done. The other way is the second method is second PWM configuration utilizes quasi-sinusoidal PWM method to control the DC-DC, and output of the DC-DC generates a rectified sine current or sine voltage at the inverter link. And then that rectified voltage is taken by the inverter, and line frequency commutated inverter unfolds it and creates the AC current. So in this case, inverter is low frequency because it only switches each half cycle of the line to unfold the rectified current. And so efficiency in this case is much better than the first case. However, in the second case, since there is no DC-link capacitor, most of the double frequency oscillation is absorbed by the input capacitor across the PV panel, making and if it is not big enough, then it can have ripple there at the PV panel side, and that will make the MPPT efficiency will sacrifice the MPPT efficiency. So big capacitance will be required at the input side in that case. Also, inverter will requires challenging control techniques to meet the THD and other grid current requirements. So comparing the pros and cons of the two approaches, the first one is preferred and mostly used, where MPPT and both MPPT and the inverter uses high frequency control with a DC-link capacitor in between. This is a typical implementation of a microinverter control stage only. It shows one example, and this is what has been used in TI reference design reference design inverter, grid connected inverter reference design. So if you look at it, it's a full bridge inverter with the LCL output. The microcontroller senses signals. In this case, it shows the bus voltage, input voltage, and the grid current, and the grid voltage are being sensed through the microcontroller on-chip ADC. The signal is taken, and then it implements the SPLL. In this case, a phase lock loop is implemented, taking the input output voltage information, the grid voltage, inverter VO, instantaneous voltage information, that is used to do the PLL function, and it shows a specific PLL using SOGI type, that is second order generalized integration type, and that is used to generate the angle reference, and then the output and the inverter that angle and the inverter reference current is fed into the multiple PR controller as a reference, and the multiple PR controller, you can see, also gets the feedback current, inverter IO instantaneous as the feedback current to each module. So through multiple PR controller and PI controller, output gets summed, and then finally a lead leg compensator followed by a fourth order notch filter implements the complete control loop. The PR controller uses here to eliminate multiple odd harmonics so that you can get good THD, the inverter current. And then, so output of the notch filter and then some feed forward, bus voltage feed forward is used in this case, and finally generates the duty cycle for the PWM modules. So that's the complete inverter stage implementation in a reference design. You can see additional auxiliary function also can be done. Sign analyzer module, in this case, used to take the input, take the grid voltage and grid current information to generate other information like RMS voltage, power, and zero cross detection, and all that stuff. So this is one example, and so we come to talk about a little bit the control loop design verification with the software frequency response analyzer. It is shown in this diagram. You can see the any power stage. It can be any power stage. It shows the buck power stage, but can be anything, DC-AC, DC-DC, or AC-DC. SFRA is able to measure the power stage response by injecting signal and collecting signal and calculating the gain and the phase using the processing power of the microcontroller, and that it can calculate the power stage response. And once the power stage response is available, you can take this to a compensation designer where you can add your control pulse and zero and gain, and look at the body plot of the loop, of the complete loop. And once the loop response looks fine, the digital controller can be generated from the compensation designer and loaded into the code, and then the code can be you run the code from the microcontroller, and that way you can verify, you can basically optimize the control loop. So it eliminates such type of tool eliminates the external frequency response analyzer, and the application and the frequency response analyzer run from the same microcontroller. It requires fast microcontroller with some kind of accelerators, such as C2000 microcontroller has trigonometric math unit that is needed for such SFRA implementation. Tune the control loop parameter in software while running the application. That gives the flexibility of that, and faster design and stable controller design can be done and measured response. So that's one tool can come handy while designing digital control loops in microcontroller application. You can see the measured versus model frequency response for the grid connected operation. We use multiple PR controller and you can see the PR controller gives high gain, very high gain, and because of that, we rejects all the higher order harmonics, and output achieves very low THD grid current in the end. So this is the THD versus different harmonic controller. It shows as we add more and more harmonic controller, the THD is improved. The last one is the one that has the different harmonic controller, and that has the minimum THD in this case. So so you can see a lot of computation and calculation is done by the microcontroller that implements the control loop, and because of that, a microcontroller with significant processing power is needed to do all the functions. Inverter phase lock loop, we talked about it, is critical for maintaining the grid current in phase with the grid voltage, and that is critical for maximizing power transfer. C2000 microcontroller has a enhanced capture module, ECAP module, that can be used to calculate the grid frequency. It can be used to detect the frequency line voltage zero cross detection. It can calculate the frequency that way. And then phase, and for the phase, you sense the voltage and you can implement the phase lock. So two diagrams are shown. Basically, it's two different approaches. One is the phase detector, loop filter, and VCO based, where the grid voltage and the internal reference is compared, and PLL is implemented using these three modules. The loop filter is actually preceded by another notch filter there. It's not explicitly shown in this case. So that is the one in the left side. And on the right side is another approach where is used orthogonal signals to generate alpha beta component, and then the power transform, and then the PLL is implemented in the synchronous reference frame using same approach, the low pass filter and the VCO there, as you can see. So two different approaches are shown. There can be many other approaches to implement the phase lock, but it requires, as you can see, much computation, generating the orthogonal signals, that transformation plus the power transformation, low pass filtering, and then the PI internal to the VCO is also requires some calculations. So the MCU that controlling this inverter stage will require processing power to do all this calculation, implement the phase lock loop. Yes, it shows the PLL equations in the same diagram, basically, on both, just drawn differently. If you look at the right side, the phase detector, it takes the reference input, PD is the phase detector, takes the reference input, and the feedback comes from the VCO, and there's the error in the phase it goes through the notch filter, and then the low pass filtering, and that feeds into the VCO. Then the VCO, the frequency, reference frequency omega 0 is applied, and from there is integrated, output is integrated, and the phase is calculated. So this is how it's implemented, the regular PLL that was shown in the previous slide, and here are the equations for the PLL implementations. So this is one type. The other one shown was the SOGI based, which is a second order generalized integration based PLL. Both requires quite a bit of computation by the microcontroller. MCU resource usage and digital control performance. For that particular example that we just showed, we just showed in the previous slides, the PR controller base. So if we run the interrupt service routines at 50 kilohertz, we saw there are 7 compensators, the PR controller basically, and notch filter, 4th order notch filter, and then it has also the software PLL for grid synchronization. It also had the ADC PWM software drivers that reads the ADC registers and also generates writes to the PWM register to generate the PWM signals, plus the SFRA, software frequency response analyzer, and the sign analyzer. All these require, if you run it at 50 kilohertz, it requires about, in that implementation, 1,500 cycles, which is about 35% of the CPU utilization on a 200 megahertz C2000 MCU, 28377 series MCU. That's about 35% of the available 200 MIPS in one core. 377S has two such cores, so total of 400 megahertz in that case. So using only one core, 35% is used, and all these 7 compensators and notch filters and PLL has been implemented while the control is running at a speed of 50 kilohertz. So the inverter, if it is 50 kilohertz, 100 kilohertz inverter, the calculation can go on at the 50 kilohertz rate, and the 200 megahertz CPU is loaded 35% in this case. The other aspect is the signal chain performance here is shown. C2000 MCU has the early ADC interrupt. So when the ADC startup conversion happens, it takes some time for the ADC to convert the signals. And while ADC is converting, you can take an early interrupt and get into the interrupt service routine, respond to the interrupt and context save. And by the time you will get into the ISR and complete the context save, you are ready to read the converted ADC signal. So that way you absorb the conversion time of the ADC into the loop and minimize the loop. So that's the feature in C2000 MCU early ADC interrupt. And that way, because of that minimization, 1, 2, 3, the steps 1, 2, 3 you can see is absorbed while ADC is converting and the result is ready. And then the control code basically is the one that for the faster MCU, it will be taking shorter time. And then finally, the writing to the PWM values is the final phase. So how this is all stitched together also will make the control loop, optimized control loop, and better response and faster response and lower TSD current, basically. So if you look at the C2000 controller at executing at 200 megahertz, there's some comparison here with an M7 running at 400 megahertz and another M7 running at 800 megahertz. The phase 4 control code implementation, since C2000 is running at 200 megahertz, if we take that as a reference one, then the 400 megahertz is basically running 2 times faster. So it will take shorter time. And the 800 megahertz will be running 4 times faster. So it will take even shorter time, only that phase 4. But phase 1, 2, 3, and 5, those has been optimized in C2000 MCU, and that's much shorter compared to the other M7 implementation. So together, the total control loop time is comparable from between a C2000 running at 200 megahertz and the M7 running at higher frequency. So that's also in the true performance takes into account the whole signal chain. It's not only the processor speed that is important, it's also the other aspects, the context save, the latch and interrupt service routine respond, and the writing to the PWM value. Those are also important in order to achieve a very fast control loop and achieve good THD in the inverter control. PID performance, you can see C28 example here running a PID in 39 cycles at 200 megahertz. It takes about 1.195 microsecond. M7 running at 400 megahertz, it takes 64 cycles and it's 1.16, comparable to C2000 running at 200 megahertz. So that's PID performance. And the table below it shows the others interrupt, ADC interrupt response. So if you look at the other phases, C2000 MCU running at C200, it takes about total 57 cycles for doing the other part of the interrupt routine, which is ADC sampling and taking the interrupt and context save and generating the PWM. It takes about 57, which is 10% of the total application. And in this case, the application takes about 537 cycles, which was run the AC induction motor control loop. So it takes the overhead here is compared 57 is 0.285 microseconds, which is 10% of the total control calculation. In the other case, same example was run using M7. It takes about 198 cycles, which is about 17% of the total cycles of 1143 total cycles. And M7 running at 480 megahertz. Okay, so that's example one. And there's an example two also here. The authors used a hysteretic current control loop with soft switching, achieving fast dynamic response and robust current regulation and high efficiency, even with higher frequency. C2000 microcontroller is used in this example. The reference is given here. And they also use hybrid modulation technique here. By hybrid, I mean bipolar modulation in the most of the case, bipolar modulation around the zero crossing to minimize the zero cross distortion, and the unipolar modulation in the other part of the waveform, as you can see, to reduce the switching frequency and without increasing the output inductance. And they also use PR controller to minimize this steady state error at low frequency and mitigate the low frequency harmonics. So this requires also on-chip analog modules like comparator subsystems. It is available in C2000 microcontroller, comparator subsystems and X crossbar, digital compare modules, and then action qualifier and deadband. You can use all these together and implement the internal the hysteretic hybrid hysteretic control using the on-chip and implement that part of the control pretty fast. So that's another aspect in the MCU can have to be able to implement this kind of hysteretic control. And if you look at the complete controller here, the authors reported hybrid hysteretic controller, and then on the reference of the hybrid hysteretic controller is generated from the PR controller here, and that's the complete current control loop for the inverter that achieves very high efficiency and low THD in this implementation. Another example is this is 3 here. The authors reported a micro inverter which uses a boost half-bridge DC-DC converter on the left side and the full bridge inverter on the right side with an LCL control here. Achieves high efficiency, high reliability. C2000 microcontroller was used in this case also. And the complete control loop, if you look at the complete control loop, is here. On the left side is the DC-DC MPPT control, boost half-bridge converter. It uses the MPPT calculation, you can see, and some damping also added, KD, and then the differential of the PV power is added to the PI output to implement the damping, and the PI controls the input voltage at the reference PV level calculated by the MPPT side. So there's the MPPT control. On the right side, it shows the full bridge inverter control, different calculation. You can see the output voltage control using the PI controller, and then that output of the PI is added to the feed forward, which uses the grid voltage and the PV power, and then that output of that is multiplied by the PLL output, and then finally reference current is generated, and then compared to the inverter current, and that current is fed into the plug-in repetitive controller, RC repetitive controller, and finally output of the repetitive controller is added to the grid input voltage, and PWM is generated. So you can see a lot of calculation involved in both stages. A digital controller with good processing power and low latency control loop can implement both of these control loop in single chip. Like a C2000 microcontroller is able to do the boost half bridge MPPT control and the full bridge control in a single chip application. So that's one consideration in implementing the control loop and choosing the microcontroller. This talks about a little bit more about the MPPT stage control. So different techniques have shown different steady-state MPPT efficiency and transients tracking. High bandwidth PWM control is adopted to track the voltage reference PV and to minimize the double line frequency disturbance in the low voltage side DC link. A capacitor voltage differential feedback is introduced for active damping of the input LC resonance. So that's the differential of the PV voltage is added to the PI output and for the damping of the LC resonance. In the MPPT, the authors reported using two different types of MPPT control. You can see in the figure here, step change and the ramp change. The step change reduces basically the oscillation in the transformer DC link flux. The step change, when MPPT uses step change, DC link flux fluctuation is higher compared to the on the right side, where is a ramp change voltage reference MPPT, where the fluctuation of the transformer DC link flux is much smaller, and that improves the efficiency and also it can prevent other inrush LC resonance and magnetic saturation of the transformer. So authors reported implementing this. This also requires some calculation. In the inverter stage, as we said, they used a repetitive controller. Instead of a pure repetitive controller, they also integrated a fourth order linear phase IIR, infinite impulse response filter, QZ in this case, integrated with the repetitive controller, and that implement very high loop gain at large number of harmonics, and that reduces the harmonic frequencies and achieves very low THD inverter current. Linear phase FIR filter can also be used, but that requires higher it can implement higher performance, but it requires higher calculation, higher filter order, and so a lot of more calculation and a maybe faster MCU can be able to implement that kind of thing. So these authors reported using this plug-in repetitive controller consisting of a proportional part, KP2 you can see, and a RC part, repetitive control part, and that achieves a high power factor and low THD current up to 13th order harmonic. Outstanding current regulation and a fast dynamic response is also reported in that paper. So C2 microcontroller is used in this case. So you can see a lot of calculation and the processing power of the MCU and the control implementation is also important in selecting the microcontroller. Power decoupling, as I said, on the DC side, there is a DC power. On the AC side, there is a double frequency. And because of that, you need the capacitor C to decouple the power, and the capacitor can be calculated from this equation. It's a pretty big capacitor. So we can minimize this capacitor, and then somehow we can use a film capacitor, more reliable capacitor. And some research was done by these authors here and implemented a active buffer, which a GaN-based active buffer. And because of that, the bus capacitance was reduced and a film capacitor could be used. So that was a research paper published by the authors here using C2000 microcontroller. Again, the control of the full buffer stage was done by the C2000 and also the inverter control. So that's something of can be considered if we want to achieve lower capacitance and high reliability, and use the MCU power, processing power to achieve that. Finally, power line communication is something also needed between the microcontroller and the gateway. So C2000 microcontroller here shows can implement PLC, which is 21 kilobit per second PLC. An example is shown here, which operation in frequency bands up to 150 kilohertz and bandwidth of 24 kilohertz. To implement that kind of PLC, C2000 is in this example a C2000 running at a much lower frequency. This is first generation C2000, 60 megahertz. It takes about 45 MIPS. So, and it does not have the accelerator VCU. So that's what it takes. So it takes about 45 MIPS out of the 60 MIPS. And then if you have the VCU accelerator, then F28069 running at 90 megahertz, it takes much lower MIPS, 21 MIPS. Basically, that means the rest of the MIPS is available for inverter control and MPPT control. So it's one example. And there's also if the processor has enough power, so you can implement the PLC plus the inverter and MPPT control, all that in single chip. So with this is the end of my presentation.
Thank you so much for the audience to join. Hope you already got what you want from the seminar, and feel free to contact TI for any other information. Thank you so much.